And once you are done with the proof at some point, don't forget to, as always, use your absolutely magnificent easy stamp. You can find it on STEMmerge. A huge thanks to Brilliant for sponsoring this video. Good morning, fellow mathematicians. Welcome back to another video. Finally, after such a long time, we are going to take a look at another hard exam. And this time it's an Australian university exam, first year exam, namely Calculus 2, basically advanced multivariable calculus and ordinary differential equations. And you might ask yourself why I would consider something like this, Calculus 2, basically as a hard exam. But there's a reason behind it, because basically everyone failed this thing in their first year of university, and the reasons for that we are going to discuss at the end of the video. But before that, I have a special guest with me. Would you please introduce yourself, Tom?
Hello maths fans, your favourite Oxford professor here, helping Jens to solve what he claims is a hard exam. But before we get stuck into the first question, do make sure to head over to my channel, Tom Rocks Maths, to see what I get up to. There's a good chance you may even recognise me from a few Numberphile videos.
Thank you very much for the nice and spicy introduction, Mr. Crawford. But before we dive into the main video, don't forget to check out STEMmerge. All the merch you can see during the video today you can find over on STEMmerge. Check it out, like the levitating globe right here or other things you are going to see during the video. We brought out a new product, which is pretty amazing. Bunch of new products. Other than that, don't forget to also watch our charity event from Christmas. It got by pretty unappreciated in terms of views, which I cannot really understand. So please check it out, for the love of God. Please check it out. We are doing this for a good cause, and I wanted to get more views because ad revenue turns directly into donations. So yeah, please watch it. Other than that, main structure of the video, as always, we are going to talk about a bit of background information, then we are going to go through all of the exercises one after another, going to give you outlines of basically the steps you need to take to solve the exercises, and at the end we are going to discuss why so many people failed in the first place and what happened exactly to not make too many people fail at the end of the day. And as always, you can download the whole exam by using the link at the top of the description. You can find it there. Also check out today's sponsor, Brilliant, who were kind enough to sponsor yet another video here on this channel. More information at the end of the video. So as a first year exam, you might imagine that a lot of people are going to participate in this whole thing. So the person who sent me the exam via email told me that around 150 students actually participated in this exam. Thing is, nearly all of them failed. There's a reason for that, which we are going to discuss at the end of the video, but if you take a look at this exam and the time you had for this exam of 2 hours, you might notice that we got a bunch of questions here, and you got 2 hours of time for that. I mean, for a first year student who is not yet used to many exams during their university life, this could pose a real problem. And it did not only pose a real problem for nearly all students, but also for a bronze medalist IMO participant. He won a bronze medal in an IMO competition, International Mathematics Olympiad, but still failed in this exam, which really says a lot about how hard this actually was. And I really wouldn't consider it to be hard. It's just the sheer amount of work you need to put in order for you to pass this exam. And now, without any further ado, we are going to dive right into the questions and see what this exam actually consists of. And the first part is going to be done by my boy Tom. Would you please proceed?
Question 1 asks us to solve the initial value problem. dy by dt is equal to y times 1 minus y, all divided by 2 minus y, and the initial condition is y of 0 is equal to minus 1. So our starting point with any problem like this is going to be to separate the variables. So we want to take all of the y terms and put them on the left-hand side. So that gives us the integral of 2 minus y divided by y 1 minus y dy is equal to the integral of dt. Now the t integral we can do directly, that's quite straightforward. So that will just be t plus a constant, let's call it c. And then the y integral, what we want to do here is turn this quite complicated fraction into a simpler set of fractions added together. So that's going to be using partial fractions. So when we do this, this will turn into the integral of 2 over y plus 1 over 1 minus y dy, and that's equal to t plus c. So now we have a much simpler integral for y, and we can do this because the first term will give us a log, so that's 2 times the natural log of y. The second term is another log, but I have to remember the minus sign, because when I differentiate 1 minus y here, I'm going to get 1 over 1 minus y, and the chain rule says to carry that minus through to get that. And that's all equal to now t plus c. Now we want to tidy this up a little bit, so we put the logs together. So the 2 becomes a squared up here, and then we've got log of y squared over 1 minus y, using our rules or laws of logs, and that's equal to t plus c. So finally, we can exponentiate both sides. So take e to the power of both sides to give us y squared over 1 minus y must be equal to some constant a times e to the t. Now all we have to do is use the initial condition given over here, which says that when t is 0, y must be minus 1. So when t is 0, that gives us a. So we just plug in y is minus 1. So then we would get 1 over 1 minus 1 is 2. So a is a half from this. So a is a half. And so our final solution then is going to be given by y squared over 1 minus y is equal to a half e to the t.
So one more piece of information, the exam actually came with extra paper for the students to write on, so they could use this space and also a blank page at next one. That's why you might notice that I'm skipping from page 4 to page 6, for example, here. So the second exercise basically is going to deal with the gradient. So let us go into the exercise. So we have someone sailing with a boat, and at some point a volcano is going to erupt. And the volcano is situated at the origin 0, 0. Shortly after the eruption, the temperature at a point xy on the surface of the lagoon is given by the function t of x, y is equal to something quotient of x and y's, where t is measured in degrees and x and y are measured in kilometers. So the first part of the exercise is going to ask for if Ushi's boat is located at 2, 1, in which direction should she travel such that the temperature is decreasing most rapidly. Give the answer as an exact third. And my initial thought here was to basically use the gradient, because the gradient is always the slope of the steepest ascent, basically, of a function. Ascent means ascending, so in the positive direction, but we want to decrease the temperature most rapidly, meaning we want to find the slope of the steepest descent. For this, we are just going to take the negative gradient of our function t. Well, and the gradient is just being defined as our components partially differentiated with respect to the component, because our t is going to be composed of some x and y coordinate, meaning our gradient or our negative gradient is just negative. At first we have the partial differential in x of our function f that we're having up here. Okay, this right here is just our function, okay, or t, whatever you want to call it, and then the partial differential in y of our function f up here. And then we are simply going to compute the partial differential, and at the end we want to find out what it is at the point, the gradient at the point. So you are basically just going to plug 2 and 1 into the x and y coordinates respectively, and then you are done. It's pretty straightforward actually. Second part of the exercise is saying that Ushi's boat is not traveling in the direction that we wanted her to go, but she's rather traveling in the direction of 7 and 12 at 13 meters per second. When it is at the position 2-1, what will the rate of change of the temperature be at that instant? Meaning we can't use the gradient anymore, but we rather have to use, because we want to find out the slope in a certain direction, meaning we have to make use of the directional derivative. Thing is, I'm not certain here if we have to use as the direction vector just 7 and 12, or if we have to use the difference or the distance vector basically between 7, 12 and then negative 2, 1, meaning overall this is going to result in 5, 11. I'm not certain about that, but one of those two it definitely is. So please leave some comments down there below and tell me which one it's probably going to be. And the directional derivative is basically just going to be defined as the gradient of the function multiplied with the vector. Let's just give this new vector a name like v, for example. And if we were to write everything out using the directional derivative, we are going to get that the directional derivative in this vector v of t is hence nothing but basically our gradient of our t multiplied with the vector components in itself, or in the scalar product you should rather say. And this is just going to result in the partial derivative in our components of t multiplied with the entries basically of the vector, so v1, and then we are going to add to it just the second part, just a simple scalar product, basically inner product of two vectors. And this basically concludes the second exercise.
For question 3, we are given a vector function, so f is equal to x minus y as its first component, the I component, and then for the j component we have x, y. Then the first part of the question asks us to show that f is not conservative. So if it is conservative, so suppose if f is conservative, then that means you can write f as the gradient of a potential. So that would mean that f would equal the gradient of some potential phi. So let's suppose it is, and then show that phi can't possibly exist. So if this was true, then the first component of our gradient would be d phi by dx, and the second one would be d phi by dy. So now we've got d phi by dx has to be equal to x minus y. And we also know that d phi by dy has to be equal to x, y. So we solve both of these PDEs. The first one, if we integrate with respect to x, we get phi is a half x squared minus x times y, and then plus some function f of y. Because if I differentiate this, I get back to d phi by dx. And then over here, this one tells us that phi is equal to x y squared over 2 plus some arbitrary function of x. Because again, if I differentiate this, the 2 comes down, I get xy, and the g of x disappears. And then if you compare these two functions, both of them must be true if such a phi exists, but we're going to run into trouble. So this has to be g of x. This term doesn't actually appear over there, and then our f of y is actually just 0. But the problem we've got is that this term is not the same as this, so this is a big old contradiction. Such a phi cannot exist, therefore f is not conservative. For the second part of the question, we're asked to calculate the integral around c of f dot dr. So this is a line integral. F is given by this function, and c is going to be, as explained in the question, the semicircle traversed anti-clockwise, so that way, from this point at 2 to this point at minus 2. So this is x squared plus y squared equals 4. So this point must be 2 as well. So we want to calculate the line integral of f around this curve. It's a closed curve, so if f was conservative, this would be 0, but we've just shown that f isn't conservative, so we're expecting a non-zero answer. Now, to calculate that, we have to parameterize our curve C. So I'm going to split it up into C1, which is the semicircular arc, and then I'm going to call the straight line C2. Now on C1, what have we got? Well, we need to have a semicircle, we need to parameterize this. So we can parameterize that with one parameter, so you write it as r of t is equal to the x component, which is going to be 2 cos of t, and then the y component is going to be 2 sine of t. Because if we now do x squared plus y squared, we get 4 cos squared plus 4 sine squared is 4. So it's exactly this curve. And this will be for t going from 0 to pi. And then along C2, our parameterization r of t. So x is increasing. X just increases from minus 2 to 2 along a straight line. So x is t, whilst y remains at 0, because the value of y doesn't change along that straight line along the x-axis. So we just have that, where t now goes from, belongs to minus 2 to 2. So now we've parameterized our two curves, you just plug these two things into our integral. So the integral will give us the following two pieces. The first one will be the integral from 0 to pi. Now, the first term in f is x minus y, so that's just 2 cos of t minus 2 sine of t. Cos t minus 2 sine t, comma, x times y, so that's just 4 cos t sine t. And then we've got dotted with dr, so that means do dr by dt, and then put the dt at the end. That's kind of how we do that. So you just differentiate cos. If you differentiate cos, you get minus sine. And then we differentiate sine to get cos. And then we just write dt at the end. So for the curve along C1, the arc, we have to just do this dot product, which gives us lots and lots of trigonometric functions, and then we're going to integrate them. And then for the curve along C2, t is now going from minus 2 to 2, x minus y, so that's just t, x times y, that's 0, and then that's dotted with dr, so dr by dt is 1, 0, and then we write the dt at the end. So now we've got the setup of the problem, we just need to do the dot product and then do the trigonometric integral, and then do this much simpler integral, because this is just the integral of t between minus 2 and 2. So this one actually will give us 0, and if you can't see that, then you can just do the integral yourself and you'll see it gives you 0. And then the trigonometric part will give us non-zero answer, because we said it's not conservative, we expect it to not be 0, and it turns out that the whole thing gives you 2 pi. So I reckon the answer to part 2 is 2 pi. So question 4 was probably my favorite on this whole exam, so I had a lot of fun figuring this one out. So we're told that we have several variables xj, which are all between 0 and 1. We're told that the sum from j equals 1 to n of these variables is equal to 1. And we're also told that we're interested in the function s, which is minus the sum from j equals 1 to n of xj, the natural log of xj. So some kind of entropy type function. And what we want to do is we want to maximize S subject to this constraint. So we want to find the maximum value of S where we are restricted by the total of these xj's being 1. Because if we weren't restricted, then the maximum is possibly unbounded. But with this restriction, we're going to have to use Lagrange multipliers, which is the method the question suggests. So the trick is setting up the problem correctly. So the way I do this is you say, I want to consider the function f, which is the thing I want to maximize or minimize. So here, this. So that's equal to s. And then minus lambda times my constraint g. So my constraint g is given by this up here, where we say that g is defined to be the sum of the xj's minus 1. So we are defining our constraint to be equal to 0. So you just ever so slightly rearrange the constraint that you're given in the question. Now, with this as our g and this as our s, we plug everything in, and this just turns into minus the sum of xj log of xj, and then it's going to now be minus lambda times g, which is the sum of xj's minus 1. And the way Lagrange multipliers work is we solve df by dxj. So you differentiate with respect to each variable, and you need that to be equal to 0, and you also solve df by d lambda equal to 0. Now, df by d lambda equaling 0, when you do df by d lambda, you're just left with that bracket. So this is actually just the same as g equals 0. So this just makes sure you remember your constraint. Now these equations, we can consider this for each j, but if we just fix j at some arbitrary number, we can see what's going to happen by just differentiating. So when we do the derivative, what I'm going to get is I'm going to hit the xj and get minus log. And then it's a product rule, so then that's going to now be plus the derivative of log of xj times xj. Log of xj gives me 1 over xj, multiplied by xj gives me 1. So with the minus sign, that's then minus 1. And then here I've got a sum of the xj's, so x1 plus x2 plus x3 plus dot 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 xj plus dot 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 xn. So when I differentiate with respect to xj, this will just give me minus lambda, because there's just a single linear term in xj from that sum. And this is equal to 0, and this is true for all j. So what we now have is an expression for the xj's, which is true for each j, and we have our constraint, which is up here, that the sum of the xj's must be 1. So this we can solve for the xj's. What we're going to do is rearrange and then take the exponential. So that will tell you that xj for each j is just e to the minus 1 minus lambda. And that's true for no matter what j we have. That's always true. And now lambda, remember, is a parameter we introduced, so we can't give our answer in terms of lambda. So we actually go back and use the constraint, or use this bit here to solve for lambda. So if each xj is the same, and is just given by this, when I sum n of them, because this is j equals 1 to n, remember, when I sum n of them, I'm going to get, by my constraint, that n lots of e to the minus 1 minus lambda must be 1. So now I divide through by n on both sides, take logs, rearrange for lambda, and that actually tells you that lambda is equal to log of n minus 1. So this gives you lambda, log of n minus 1. So that goes back into your formula for xj, And when you simplify everything, the xj's are actually just equal to 1 over n. So to maximize the value of s, given by this function here, you just plug in xj is equal to 1 over n for each xj.
Thank you, Tom. Next up is the fifth exercise. We have some function given and its graphical representation as a surface S in three-dimensional space. And the curves R1 and R2 are given by some vectors, basically. Both lie on S and pass through the point P being equal to 0, 1, 1. Calculate the equation of the tangent plane of f of x at P. Give the answer in the scalar form ax plus by plus cz is equal to d. So the way to go here is to find at first our tangent vectors. This is basically the algorithm you need to go through. To find the tangent vectors, at first you want to find out what values for t and you need to plug in such that R1 and R2 are going to be equal to our point P being equal to 0, 1, 1. So let us rewrite R1 at first, which is nothing but t squared and then t plus 1 and at the very end 2t plus 1. And let's see for which values of t we are going to find out when this is equal to 0, 1, 1. And this is fairly straightforward. I mean, t squared can only be equal to 0. It's an idempotent if t is equal to 0 in the first part, meaning we need to have t being equal to 0. Next up, we need t to be equal to 0 yet again. And at the very end, we need to set t being equal to 0 once again to get ourselves, well, just the point P. And now for the second vector R2, we need to find a value for u, which is going to result in our point P yet again. So which value for u is going to result in this vector? Let us take a look at the 0 component. I mean, we just need to solve u to the third power minus 1 is equal to 0. At 1 on both sides, u to the third power is equal to 1, meaning u must be equal to 1. Meaning this is going to result in 1, 1, 1 probably. Let's check for the other components. If we plug in the second component 1, this fits. Okay, 1 is equal to 1. And plugging 1 into the last component 1 minus 1 is 0 plus 1 is going to give us 1. So this right here does hold. And now we can proceed to find the tangent vectors, meaning just as always to find the slope or the tangent at a certain point, we are going to differentiate our vectors component-wise. Meaning we are going to differentiate R1 with respect to t on each and every component and R2 with respect to u on each and every component. And then we are going to plug in the values for u and t respectively that we just found out, so t being equal to 0 and u being equal to 1, and then we find out what our tangent vectors must be. So t squared is going to turn into 2t, and then we're going to have 1 and at the end 2. And plugging this in for t being equal to 0, this is going to result in 0, 1 and 2. This right here is our first vector, very straightforward, and you can do the same thing for u. Now that we are done with those vectors, we just need to take them into a cross product, and all that's left to do after that is to plug our cross product vector basically into our equation. So each and every component are going to be the coefficients a, b, c, and we are going to possibly get a d out after doing some manipulations. And also we need to subtract from each and every x, y, and z component the components of our vector p that we had at the beginning, our point p. And this is the basic algorithm to get all of this done. Like mentioned before, our components of the cross product are just going to be our coefficients of our planar equation basically. So meaning we are going to get -3 times and now x minus the first component of our point P, which is 0. Now we are going to continue with this process. Plus 6 is the next coefficient times y, and then we had -1 overall. And last but not least, we are going to have -3 times z minus 1 being equal to 0. And now we can factor everything out and then bring stuff to the other side, and this is going to result in our answer.
Question 6 gives us a function of two variables, f of x, y, which is going to be equal to xy minus x plus y minus 1 times e to the minus xy. And we're asked to find the maximum and minimum values of this function on a particular domain. And the domain we're interested in is a triangle with vertices at -1, 0, another vertex at -1, 1 up here, minus 1, 1, and the other vertex on the y-axis, so that's going to be at 0, 1. So we join them up to form this right-angled triangle, and then on that domain we want to find the max and the min of this function. Fortunately, I made a very recent video on exactly how to solve problems like this, because here we're trying to find the critical points, the max and the min, of a function of several variables, and we do this by solving for the gradient of f, or its two partial derivatives, equal to 0. So if we calculate df by dx first, so I make that to be, we're going to do a product rule and get y minus 1 times the exponential, and then it's going to be plus the big bracket, xy minus x plus y minus 1, and then times the derivative of the exponential minus y e to the minus xy. And then we do something very similar for df by dy, and that gives you x plus 1 e to the minus xy plus big bracket times minus x e to the minus x y. And we want both of these to be 0 at a max or a min, or possibly a saddle. Now, for both of these to be true, we can first of all say that the exponential clearly is never 0, so that cancels from both terms. And then we've just got now two polynomials in x and y that both have to be equal to 0, so we can solve both of those simultaneously to find the values of x and y that make this possible. So we can actually rewrite this first equation as y minus 1 squared is equal to xy times 1 minus y, just tidying up the equation a little bit. And the second equation becomes x plus 1 squared equals y times x plus 1. So now it's much easier to see how to solve this system of equations, because here we can either have that y is 1, and then that would make both sides of the equation 0. And here we could have x as minus 1, would make both sides of the equation 0. And there are other possible solutions that would also work, but when you check them all, it turns out that in this triangle, it's just those two that I mentioned that actually give you a critical point within the triangle. So you can check all of the others, but they're just not within that triangle. So within our domain, the only critical point, which we don't yet know if it's a max, a min, or a saddle, but the only critical point occurs when y is 1 and when x is minus 1. So we know that when y is 1, x is minus 1, we have a critical point. Now, if you plug those values into f at that point, at minus 1, 1, so up here, it actually has the value 0. So you sub in, you get that that's 0. So again, we still don't know if this is a max or a min, but if you also consider f at minus 1, 0 and f at 0 and 1, it's also equal to the value 0. So it turns out that this is actually a maximum point. And you can check this using the method of the discriminant, which I also talk about in a recent video, or by calculating second derivatives and various other things. So this is in fact the maximum value of f on this domain, and it occurs all the way along this edge and along this edge, as well as at this corner point. And then the function itself, with a little bit of thought by looking at it and considering the range of values of x and y, what's actually happening with the function is you have the value 0 along these edges, and then it kind of slopes down away from that point. So the function is very much decreasing away from all of those, both of those edges. So the function is kind of sloping away And so the minimum value is actually going to occur here at minus a half. So f at minus a half, which when you plug in those numbers, you'll find is equal to minus e to the 1/4 is the min value.
Now number 7 is one exercise that I'm pretty familiar with. This is just dropping a ball or a mass or whatever from a certain height, okay, with air resistance. So basically a force is going to act on this ball. This is why we have this m times a term right here. And this is equal to two forces going against the main force, okay? Which is going to be the gravitational force. And then we have some damping term because we have some air molecules going against our mass, meaning we are going to have damping involved. And the first exercise tells us to calculate the solution for x of t subject to the initial conditions x not being equal to h and x dot not is equal to 0. And for this you can use various methods. I'm going to present you the outlines of one and then you can go through all the calculations yourself. So at first I would like to divide by m on both sides here on this equation, leaving us with x double dot being hence nothing but, and then we are going to have negative g and then plus k divided by m times x dot. And you can basically at first solve a homogeneous equation, and after that you can go ahead and solve for the particular solution of the differential equation, getting yourself the general solution to the differential equation, but you can actually make it easier by doing a change of variable here. So what you're going to say is that our x dot is nothing but z. This means if we differentiate both sides with respect to t, we are going to get that z dot is nothing but x double dot. Meaning this is going to result in a reduced order differential equation. Namely, we are going to have that z dot is hence nothing but negative g k, so plus k divided by m times z. And now we can divide both sides by this term, leaving us overall with z dot divided by negative g plus k over m times z being equal to 1, and now we can just integrate both sides with respect to t. And then you can go through the whole process, leaving you in the process with some function z with respect to t, okay, just integrating both sides. This is how differential equations work, being equal to something exponential term. Definitely this is going to result in an exponential term because you are going to get the logarithm out on this side in some way, logarithm or something, and then you exponentiate both sides, leaving you with some kind of e snack, basically just some constant multiplied with an exponential term. Probably k divided by m times x in some way, no t, not x, plus some arbitrary constant c. And then you can go ahead and say, okay, z of t was nothing but your x dot, and then you can just integrate both sides yet again to get yourself the final expression for x with respect to t. It's very straightforward. It's really easy to separate and solve this differential equation. And then you can just plug in the initial conditions, meaning in each and every t you are going to plug in 0. You are already going to have the equation for your x dot right here, making everything way easier, meaning x dot of 0 is going to result in just this constant plus this constant basically. And then you can go ahead and just solve for the initial value problem. Second part of the exercise says that you have to determine an algebraic equation for the time taken for the particle to fall to Earth and calculate an expression for the impact velocity. This is also extremely straightforward. Let's go through the process a tiny little bit, meaning we are going to have an initial height h right here where the ball is going to fall down, basically our mass m on a height h. What is going to happen if we hit the Earth? What is with the height h? I mean height h is going to be 0 when it hits the Earth. Meaning we are going to just say that h is going to be equal to 0 in our problem that we already solved for the initial values. Meaning you are going to take a look at x of t where h is equal to 0, and then you are just going to separate for t. Once you have solved for t, you are going to go into this equation of x dot and then basically just plug your t in, and then you can basically get yourself the algebraic equation. Okay, if this right here is our t naught, for the time it falls to the Earth, you're just going to plug the t naught in, and then you're going to get another solution for an initial value problem, solving for the velocity in the process. And this concludes the exercise. Now off to number 8. Now number 8 is actually fairly easy, at least the first part. So we have to prove the inequality something something, and consider what happens when both sides of the inequality are squared. So in the normal case, if you square both sides of an inequality, for example, if you have negative cases, -3 is less than -2, and if you square both sides, you're going to get 9 and 4. Okay. Or the relation is going to change. But if we have positive values, for example, 3 is greater than 2, if you square both sides, then we have 9 is greater than 4, obviously. Meaning, if both sides of an order relation are actually greater than 0, or greater or equal to 0, then we can square both sides and the order relation really doesn't change. And this is the case. I mean, our third is strictly positive, okay, obviously, since it can be complex, z is strictly greater than -1. And this part right here, by this condition that we're having here, is obviously also positive, because z/2 is, even if we have the lowest case, like -1, basically, we're going to get just +1/2, and the higher we go, okay, in the more positives it's going to stay positive. Meaning if we square both sides, we're going to get 1 plus z is less or equal to, okay, and by the binomial theorem, we are going to get 1 plus z plus z squared over 4. And now you might notice something, namely that 1 plus z and 1 plus z is going to cancel out, meaning what we have to prove is 0 is greater or equal to z squared over 4. And obviously this holds. Doesn't matter which value for z you are going to plug in, you're going to have that z squared divided by 4 is going to be positive, because z squared is a squared, and by definition it's going to be positive. Now, next, we are going to use the inequality in 1 to construct an epsilon delta proof for this multivariable metric limit. Okay, and one good thing here is students didn't really need to remember all of this, because there was actually a cheat sheet coming with this exam. And they actually put the epsilon delta definition into here, which I find to be very generous of you. Thank you very much, lecturer. And basically, we are going to take a look at what happens with our metric, with our Euclidean metric here in this definition. And then we are going to use the inequality to kind of conclude a delta for us, like a upper bound, basically. Okay, so in our metric right here, we are going to plug in what happens when a and b are going to be plugged into here. Now, a and b are 0 and 0, meaning our metric in our process is going to turn into the square root of x squared plus y squared. This is something that we need to use later in the process. Here was my thought process when constructing the epsilon, basically. So for this, we need to take a look at our function f. Minus our limit L, but our limit L is going to be equal to 0, so the absolute value of our function is going to be the absolute value of what we have here. So the square root of 1 plus 4x squared plus 2y squared minus 1 divided by square root of 4x squared plus 2y squared. And my thought process here, I didn't go through the whole thing, so my initial thought was to use the approximation here on this step already. Because this term that we're having up here is of the form 1 plus something, meaning this right here, by our definition that we are having here, is going to be less or equal to the absolute value of, okay, our 1 is going to stay here, plus, and then we are just going to take what's in parentheses over 2, so meaning this is going to turn into 2x squared plus y squared minus 1 divided by square root of 4x squared plus 2y squared. 1 and -1 is going to cancel out, and now you can proceed and use this rationalizing of the denominator trick, basically. We are going to multiply top and bottom by the square root of 4x squared plus 2y squared. Really doesn't matter if you have absolute values here, because the third is being defined positive. And if we were to multiply everything out, we are going to get. And one thing you might notice is that this and this factor is going to cancel out, leaving you with the square root of 4x squared plus 2y squared over 2. And then you can probably proceed and make use of what we have found out here in the metric as the delta, and probably use it to finish up the proof. And once you are done with the proof, at some point, don't forget to, as always, use your absolutely magnificent easy stamp. You can find it on STEMmerge. Ninth exercise is one I'm not too familiar with anymore. Nonlinear dynamics was quite a while ago, but I'm still going to give it a shot. So we have the logistic equation given with harvesting, and we have to identify all the fixed points, equilibrium positions. Fixed points means we want to find solutions P star which are constant, okay? This is just some p with respect to some time. And if we were to differentiate a fixed point, since p star is nothing but a constant, we are going to look for solutions of dp, dt being equal to 0. Meaning we are just going to set this equation equal to 0, and then we are going to solve for all the equilibrium positions. Meaning this right here is going to turn into a second order equation, a second order polynomial, second degree one, and where you can just solve it regularly. And then you are going to get yourself 2 fixed points. And in the next step, we have to identify all the fixed points or equilibrium solutions which are stable, and you have to justify your answer. And like I said just now, you're going to get 2 fixed points, P1 and P2, and for the logistic equation it is mostly the case that only one of those 2 is going to be a stable one. So in a normal case you are probably going to draw yourself some kind of graph, and then you are going to have a graph like this, where we have this one fixed point right here and the second fixed point, and basically we are going to have something like this given. No, this one right here should be, okay, by just argumentations that you find in nonlinear dynamics. I can't go into too much more detail right here because it would take ages to explain. This right here is going to result in an unstable fixed point. And this right here is going to be a stable fixed point. But we can also have the other situation, namely our third cannot be imaginary. This is not something that is going to, our discriminant can be a negative, meaning our thirds can't be really imaginary. This just has to do with the fact that our population size would then be negative, which really doesn't work, meaning we only need to consider the cases when we have 2 states, P1 and P2, or when P1 and P2 are equal, meaning our discriminant is equal to 0. If those 2 are equal, we are going to have one fixed point, and this fixed point should be an unstable one. Once again, and you can probably just argue using those diagrams that those are stable and unstable fixed points. This is how you go about something like this most of the time, but you can also justify your answer using limits, basically, by finding out how your differential equation, your nonlinear one, acts under those fixed points, and then find out what happens in the limit. And the last exercise here is going to be if we plug in 2 values, so for r and k, we want to find out for which value of h does a bifurcation occur. And bifurcation basically just means in 1 or 2 dimensions that we want to see when the stability of some fixed points are going to change. Meaning what we can do is we can, for example, drag those fixed points downwards and turn a stable fixed point, which was here, into an unstable fixed point. This is something that could happen. Meaning what we are going to do is we are going to find some value h for which P1 and P2 are going to be equal. And thus the stability is going to change, because we know that this right here is going to be an unstable fixed point, but this right here before was a stable fixed point, and then a bifurcation does occur. This is just the case for logistic maps, basically. And yeah, this is the process you need to go through, and this right here really involves heavy calculations.
Finally, for question 10, we are given the solution to a homogeneous differential equation, and then asked to solve a very, very similar inhomogeneous differential equation. Now, the way this works is as follows. We are given the solution to y double prime plus 8t y prime plus 4 times 4t squared plus 1 times y equals 0. And we're told that a solution to this is y equals e to the minus 2 t squared. So this is a possible solution to this equation. Now the question says to use the method of the reduction of order to solve the inhomogeneous equation. So what that means is you try a solution y equals u of t, where u is at the moment an unknown function, multiplied by our known solution, e to the minus 2 t squared. So now you calculate y prime, which I'll do this one, that's u prime e to the minus 2 t squared. So product rule, then it's going to be minus 4t times u e to the minus 2 t squared. And then we also calculate y double prime, I will leave that as dot, dot, dot. And then you plug all of those into the equation, and what actually will happen because of this method of reduction of order, we just get back something very, very simple. So when you sub in, you actually just get that u double prime is 0. And that's it. So now you solve this and say, well, u is clearly just a linear function, at plus b, and so therefore the most general solution is at plus b times e to the minus 2 t squared. So we have the most general solution, y equals at plus b e to the minus 2 t squared, for the homogeneous differential equation. But we're asked to solve the inhomogeneous one, where this is equal to e to the minus 2 t squared times cos of t. So as with most ODEs, what we need to do is take our homogeneous solution and add on the particular solution, which solves the equation equal to e to the minus 2t squared cos. So for that, you try another solution, which is going to be equal to c times cos of t plus d times sine of t times e to the minus 2 t squared. And what you want to do again is calculate y prime equals dot, 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 calculate y double prime. These are really annoying to do, so leave that one as an exercise to the viewer. And then substitute those into this, and now evaluating it equal to e to the minus 2t squared cos of t. And when you equate the coefficients, you'll see that your c here, c must actually be minus 1, and d must be 0. So your overall solution is the homogeneous one plus the particular solution we found down here. And so the very final solution is y equals at plus b e to the minus 2t squared minus cos of t e to the minus 2 t squared.
And this basically concludes the outlines of all the exercises. And now, after looking through all the exercises, you might already know why so many people failed in the first place. Thing is, if you're a first-year student and you never did any kind of exam during your university life at all, it's going to pose a real problem to you if you want to try to solve 10 of those questions which just involve so much heavy computation in 2 hours. That's really hard to do. I can understand why so many people fail. And even if you are a winner in the IMO, it doesn't mean that you are fast at problem solving and getting all the computations done. And this is something I can really understand. And in order to make not too many students fail, so to get a passable rate of students actually completing this exam, the lecturer had to downgrade from 40 marks that you would need to possibly get to pass to 25 roughly. So he really put a nice spicy curvature to this whole thing to make at least some students finish this up, which is really crazy. 25% in an exam is not much that you need to get in order to pass. So he really had to adjust the curvature by a huge margin. And I respect it. Thank you, professor, for making at least some students pass, but give them more time, please. Don't put in so many exercises and give them more time. They are first years. They are not used to doing exams like they have to do at university. It's just not something they do on a regular basis. So please, be a bit more chill at the start of university. Don't let them leave, okay, at the start. They want to become something, so give them the chance to become something. And this basically concludes the video for today. But before you end watching the video, don't forget to check out today's sponsor, Brilliant, who are kind enough to sponsor yet another hard exam video here on this channel. Today's exam was one of a different kind, covering essential knowledge from the first 10 years of school and a massive amount of various university level topics. As easy as some of the questions might seem to math enthusiasts like us, under the circumstances that they were presented with, students considered these questions to be really challenging. We all started out small once, so never forget your fundamentals. If you're interested in brushing up on important topics or clever math, calculus and high analysis, I encourage you to try out Brilliant today. Besides their awesome selection of various problems in mathematics, geometry, physics and many more topics, Brilliant provides their subscribers with dedicated single and multivariable calculus courses, as well as differential equations. It covers the most basic and important math topics to really get you prepared for your next exam or upcoming studies. I don't know if you already thought about your New Year's resolutions, but if you haven't done so already, then definitely consider to get yourself a premium subscription for Brilliant, because one of those New Year's resolutions could be that you would like to learn a new topic. For example, one New Year's resolution, I want to learn a new topic in various mathematic topics once per month. This month I want to learn multivariable calculus, next month I want to learn about linear algebra. All those topics one after another, brushing up on all the most important fundamentals one after another. And this is something I encourage you to do. And if you want to really get yourself some New Year's resolutions that you could really benefit from, then make sure to check out the link at the top of the description. With it you can already access Brilliant for completely free, okay, at least a big portion of it. And the first 200 people to actually use the link get 20% off an annual premium subscription. So definitely try it out and support the channel this way. If you enjoyed this video, then please like, subscribe, make a comment, channel flag. Don't forget to also subscribe to my boy Tom Crawford, who was kind enough to create yet another video here for this channel together with me, and I really enjoyed his participation in this video. And yeah, definitely subscribe to him, link to his channel at the top of the description. Other than that, don't forget to check out STEM Merch, and up until next video, I wish you guys a flimble day. Please share the video if you did enjoy it. Ciao!